Hello guys, this is chapter 2, Motion in Two Dimensions. In this chapter, we're going to apply all the knowledge that we learned in chapter 1, but this time in two dimensions. Here are key concepts of this chapter. After completing this chapter, you should be able to explain the difference between a vector and scalar quantities, solve vector problems involving distance, position, displacement, acceleration, describe how to determine total displacement in two dimensions using two methods, scale graph diagram and a component method. Solve problems related to horizontal and vertical displacement of the motion in a projectile using kinematics equation that we learned in chapter 1 by determining the range, which is a horizontal displacement, maximum height, vertical displacement, final velocity, magnitude and direction, and time of flight using quadratic equation for a projectile motion. Assess the social and environmental impact of the technologies that are applied using those concepts. This is section 2.1, motion in two dimensions using a scale graph diagram. For this section, you need protractor, ruler, paper and pencil, and be ready actually to practice. Please pause the video, get those ready, and time after time you have to pause the video and do it yourself. This is the best way to learn. We're going to learn how to express the direction in a coordinate system. The coordinate system, we can use it the same way as we use it in math, as an X and Y coordinate system. However, we can use north, south, east, and west as well. So the common thing between those two coordinate systems is that they are perpendicular to each other. So if the vector is drawn in that coordinate system, you should be able to describe the vectors in two-dimensional or resolve the vector in two dimensions. And we can express it how this vector is in respect of this coordinate system. For example, here is a coordinate system, north, south, east, west. They are perpendicular to each other, and each of those quadrants have a 90-degree angle. So there is a vector A, vector B, vector C, vector D. How can we express the direction of those vectors so every one that you can tell to draw, ask to draw a vector A, should be able to draw exactly the same, no matter how you are going to describe it? So, as a matter of fact, there are 4 ways to describe that direction of the vector A. For example, if you want to start from east and you have to move toward to that direction, how many degrees you have to rotate, you have to move? It has to be 35 degrees. So you can express it east, you move toward north 35 degrees. So everybody understand you can draw a 35-degree angle 35 degree, and then you draw a line which is a vector A. However, what about if you start from north? There's nothing wrong to start from north, but you have to say it, what is the angle? But this angle now is not 35 anymore. It is 90 minus 35. So that one actually is going to be 55. So you can express exactly the same vector, now slightly differently. North, 55, east. So those two directions with a square bracket, actually, they are mostly used in physics. But in everyday, we don't say it like open bracket, east, 35 degree, north, close bracket. We just say it as a 35 degree north of east. Or if you move 35 degree east of north. So you should be able to know all 4 of them Not because you have to express and say it every time 4 ways a vector, but you should understand in any ways that is given to you, you should be able to draw a vector. For example, vector B. Vector B starts from south, 12 degree. So we can write it south 12 degree toward east. However, what if we start from east? So it's a 90 degree minus 12 is 78. So we can say east 78 degree toward south, or 12 degree east of south, or 78 degree south of east. Vector C, it is really maybe easier or maybe confusing because 45 is half of 90. So no matter where you go, where you start from, it is going to be 45 anyways. So it's going to be, if you start from south, it's going to be south 45 west. And if you start from west, it's going to be 90 minus 45, which is 45. So west 45 south. And the last one would be D. D is 80 degree from west. So you can write west and you move 80 degree toward north, or what is 90 minus 80 is 10. You start from north 10 degree toward west, or 80 degree north of west, or 10 degree west of north. We need to know the properties of vectors because sometimes we need to combine vectors together in order to describe the position of the object in 2 dimensions. We'll determine the object 2-dimensional displacement using different methods. One is a focus of this section. It's a motion in 2-dimensional using scale graph diagram. So what is important here is to draw a vectors based on a certain scale accurately based on their magnitude. So the magnitude is important, but direction also is important. That's why I said you need a ruler and you need a protractor for this lesson. So if we have to add 2 vectors and find a total displacement, so we need to draw vector delta d1 and vector delta d2 based on proportional scale and accurate angle between them. And the next one, it is algebraic method, which we call it component of the vector method. You should know how to draw a vector properly with a magnitude and direction, because sometimes when you add vectors in 2 dimensions, vectors will not necessarily be pointing toward north, south, east, or west. They might be pointing at a certain direction, so you have to draw accurately the angle. So resultant vector is a vector that results from adding 2 vectors, 2 or more vectors together. So there are 2 ways actually to add vectors together. We mentioned that tip to tail before in the chapter 1, but there's another rule that is a parallelogram rule. It's more covered in grade 12, but I'm going to just cover that anyways. So what will happen if you have 2 vectors? Vector D and E. How can you add those 2 vectors? They are from the same origin. They start from the same origin. So in order actually to add those 2 vectors, you can add them using a method of tip to tail. So that means that you can place the tail of one vector to the tip of the first one. So what do you do? Here's a vector E, and you can move that vector E parallel to itself. Same magnitude and parallel to itself. And then you place it exactly where the vector D ends, to the tip of the vector D. And then a rule is the same for 2 or many as you want. So you can place a resultant where starting from where the first vector start to the tail of the vector, first vector, toward where the last ends, so that to a tip of the last vector. I'm saying last because you can add as many vectors as you can, as long as you place them one after the other, etc. Another actually rule is a parallelogram rule. The parallelogram rule is useful when those two vectors are starting from the same origin. So actually you don't really need to move anything. You just draw a parallel from the tip of one vector parallel to other vector. For example, you draw a parallel from a tip of D parallel to E and from tip of E parallel to D. So when they intercept, then that is a tip of the resultant. So make sure that you draw a parallel from the tip of each vectors, and when they intercept, that will be a tip of the resultant vector. I have seen people doing that mistake, just drawing a line, joining two tips, but that will be wrong. That is not a sum. So this sum, this total, has to be exactly the total that you are using. Whatever method you are using, resultant has to be the same. Otherwise, if that's not the same, the method is wrong. What you're doing is wrong. The resultant has to be exactly the same. Now here's a practice. So you place the tail of the second at the head or a tip of the first. That's a rule. You do that, you'll do adding vectors always correctly. So the total or a sum has to point from a tail of the first vector to a tip of the last. One more time, you have two vectors. Now they are not starting from same origin. Same thing. If they are not starting from same origin, you draw one vector as it is, or basically leave the vector where it is and move only one vector parallel to itself and place it the tail of the vector 2 to a tip of the vector 1, and then you can join tail of the vector 1 toward tip of the vector 2, and that will be always correct if you do follow that direction, that rule. Now, as I said, you can have more than two vectors. That's exactly the same. I mentioned that many times. If you have a vector A here, and you can place a vector B where the vector A ends, and you can place a vector C where the B ends, and then vector total or a sum of A plus B plus C is a vector D that start where the vector A start and join where the last vector, that in this case vector C, ends. And you will never make mistake if you follow that rule. To draw a two-dimensional vector using a scale diagram, we need to determine the reasonable scale. For example, if we need to draw a 15-meter vector, you don't have a 15-meter paper to draw it. So you have to decide what would be a reasonable scale to use in order to draw a vector in a paper, so that vector has to represent a 15-meter vector. For example, if you have a 15-meter west 35-degree north, you have to use a scale that is 1 centimeter for 5 meters. So you have to write it down. So when you draw it, you have to draw it 3 centimeters, because that length represents a magnitude of that vector, 3 centimeters, and you have multiplied by 5 is going to be 15 meters. However, you can change the scale as you like For example, if the 3 centimeter, it is too long to draw for the space that you have, you can use a different scale, like 1 centimeter is equal 10 meter. So now you can draw the same vector, but this time has to be 1.5 centimeter, because when you measure back, it's going to be 1.5 times 10 meter is going to be 15 meter. So that has to match. Now for angle, that's why you use a protractor. So angle has to match too. So what do you do? From west, you draw a line, a very light line, 35 degree toward north. Then you measure it, that the vector in that line, 1.5 for scale 1 centimeter with 10 meter, or 3 centimeter for the scale 1 centimeter with 5 meter. Then you can draw a hard line with an arrow that represent the vector, which is 15 meter west, 35 north. Sometime you might have more than one vector to draw. So let's say that you have 540 meter vector. You can use a scale 1 centimeter with a 100 meter, and you can draw 1 centimeter, 100 meter. That means you can draw 5.4 centimeter vector that represent 540 meter. But if you have another vector here, you have to consider that as well, because that scale that you decide has to be exactly the same for the second vector or for total vector, because that scale has to be 1 to show the vectors proportionally. If the vector delta D1, for example, is smaller than delta D2, you draw delta D1 with that scale to show to be shorter than delta D2. Let's give you an example. If you have 540 meter delta D1 and have 700 meter delta D2, you can draw with the same scale 1 to 100, 5.4 centimeter delta D1 and 7 centimeter for delta D2. So that scale has to be the same for the set of vectors. So that's what I said, is a scale chosen has to accommodate all vectors in diagram. Exactly the same to show proportionality. Which one vector has a bigger magnitude than the other. At the end, after finding the total displacement, you draw it, and I'm going to teach you how to draw it shortly. You need to convert the value back to the original unit. You cannot express something like this. First displacement is 540 meter. Second displacement is 700 meter. And total displacement is 400, for example. Depends on the angle, obviously. It's a 400 meter. So you cannot say that delta D total is 4 centimeter. Yes, you draw it, that is 4 centimeter. You measure it, that is 4 centimeter. But you have to convert it back to original units, which was meter. And the scale was 1 centimeter with 100 meter. So let's say that total happened to be 400. You have to say that total is, if happened to be that total is 4 centimeter in your diagram, then you have to say that total is not 4 centimeter, but is 400 meter. So in this example, the scale that I use is 1 centimeter with 100 meter, and you have to write it and follow that scale for all the vectors involved, not just one. To summarize it, to draw two-dimensional vectors using a scale diagram, you need to determine the reasonable scale for the diagram to accommodate all those vectors, to have into consideration the magnitude of all vectors. So those vectors, when you draw, has to fit to the space that you have in the paper. For example, if you have a scale 1 centimeter with 10 centimeter, that scale has to apply to all of them, including total displacement, total or resultant vector. So at the end, after finding that total displacement, you need to convert it back to the original value using the same scale. So if that total is 5 centimeter, for example, you have to say 5 centimeters, since that scale is 1 centimeter, 10 meter, now that vector has to be 50 meter. Here is one example. If you have to draw a vector delta d1 and delta d2, you know exactly that delta d1 is shorter than delta d2. And you can say that delta d1, it is east 35 north. Delta d2 is east, so the delta d total is the line that joins where the delta d1 starts toward where delta d2 ends. You join it, you measure it, and you scale it back. You convert it back to the original units. And for this, you need practice. And for this, you need to have a graph paper or any paper per se. But the graphing paper is easier because we'll make right angle triangle easier for you to draw. And another thing that I mentioned at the beginning is you need a ruler and protractor to do assignment for this chapter. We learn about vector additions, how to add vectors together using tip to tail. What about subtracting it? That's pretty much the same. The only trick here is you can do vector d is equal a plus minus vector b. So in order to subtract b from a, you add minus b to a. So you can draw a, and then you can draw minus b. Then you can follow the same rule, tip to tail. So you place vector minus b where the vector a ends, and then draw a vector resultant, which is d, or a minus b, which starts where the vector a starts and ends where the vector minus b ends. Here's a summary of the vectors. You can just go over and read and practice of this. So if you have two vectors that are parallel with each other and have the same magnitude, same length, that means that vector A has to be equal to vector B. You learned already vector addition. So you can place the vector B where the vector A ends, and sum of vector A with B is a vector C, which starts where the vector A starts and ends where the vector B ends. The reverse of the vectors, we already learned that if you flip the direction, that will be a negative of the previous one. So when we subtract a vector, you flip that vector to make negative. For example, vector A and vector B are the same magnitude but in opposite direction. So we can say, so vector A is equal to vector minus B, or as a magnitude of vector A is equal to magnitude of vector B, if in case you need to draw it like that. Vector subtraction, we just said it, so you do exactly the same thing as a vector addition, but you add the reverse of the vector b to a vector a. So instead of saying a minus b, you can say a plus minus b. And last one, actually, if you want to multiply the vector with a number, that means that if the number is bigger than 1, then the magnitude is going to be multiplied by that number that you want to multiply the vector. But remember, if the number is a negative, then it's going to produce a vector that has a bigger magnitude, obviously, but the direction is going to be flipped on opposite direction because of that sign in front. So if you want to multiply a vector with 3, for example, that is going to make a vector 3 times longer. And if you want to multiply a vector with a negative 3, again is going to make a vector 3 times longer, but it's going to be in a reverse direction, in an opposite direction. That's about summaries of vectors. Here is the time that you have to practice in order to learn how to draw a scale graph diagram. At the beginning, I told you to get ready with a protractor, ruler, paper, graphing paper if you want, and practice. It's not about learning or reading or listening or watching. It's about practice. Okay, so a ball undergoes a displacement of delta d1 6.2 west 25 south as they approach the wall. It bounces off with a delta d2 equal 4.8 meter west 25 north. The whole motion takes 3.7 seconds, that is the time. Determines squash ball, total displacement, and average velocity. So you don't need to calculate displacement using any math algebraic method. You have to draw it. Then when you determine displacement, average velocity is easy. You can just divide it by time and you get the average velocity. Let's start working. And if you're not ready, pause the video, get things ready, and then we can start doing things together. So the first thing, you have to determine the scale. Remember, scale, because you need to fit those vectors in a paper that you have there, the space that you have on a paper. I chose to be 1 centimeter is equal 1 meter because I can draw 6.2 centimeter and 4.8 centimeter easily on my paper here. Okay, but that's not all, because another important thing is to determine where those vectors are, in which quadrant. Because if you decide to use that coordinate system in the middle, so that means that you are starting here in the middle, you're going out and you're going outside. So that's why you need to determine in advance how to use it. So you can draw something here in outside or in a piece of paper in advance to know exactly what happened. Then next step would be draw a coordinate system. The coordinate system is exactly what it needs to be by leaving the whole space in the quadrant 3, because I know that where the vectors will be, and less on quadrant 2, because maybe that vector might go above the line, so I need a little bit space there. I don't know exactly, and maybe a little bit here in case. I'm not sure, but definitely nothing is going to be on quadrant 1. So that's the next step that I do, decide how to draw a coordinate system. After drawing the coordinate system, I need to measure the angle for vector delta D1. West, 25, south. So pretty much is going to be between west and south. It's going to be somewhere here, but has to be absolutely accurate. So that's why you use a protractor. So then you can actually count 10 degree, 20, 25. So I put a dot here and I draw a thin line so I can have a line now to measure later. So I measure the angle, and that is a very important step. Next step would be measure the length of the vector itself. So I use a ruler to measure 6.2 centimeter. So make sure that it's very accurate because 1 millimeter is a lot. So 6.2, and then I draw and label it. I draw. So how can we add a next vector? Remember tip to tail? So the second vector has to start where the tip of the first vector is. So that's why we build a new coordinate system exactly where the tip of the first vector is. Remember that, I warn you, this is a common mistake that people do by just not drawing that second coordinate system. And they just draw a 25 degree, for example, based on delta D1, and that will be wrong. So you draw a second coordinate system where that tip of the vector 1 is, because there is going to start a vector delta D2, which is going to measure between west and north. So it's going to be something in that direction, but has to be accurate. So that's why you need a protractor. Then you count. You count from 0 here to 10, 20, 25. You put a dot here, and then you can draw a line. And that's how you measure 25 degree from west toward north. Next step would be similar to what we did at displacement delta D1. You measure it and draw that vector and label it. Now you are ready for a final step, and final step is how the total displacement is. It starts where the first vector starts and ends where the last ends. So you have to draw a line here to join those 2 points. So just start from where the first started toward where the last end. And then you draw a vector, and then you measure the length. That is exactly what you do. You measure the length, which is approximately 10. That's what I'm saying. You have to draw it as big as possible to see the difference, because 9.9 and 10.1 is a big difference. So measure the length and convert it back to the unit that you started with. Remember, 1 centimeter is equal to 1 meter. So now we have 10 centimeter. So we cannot say is a 10 centimeter as a total displacement. You have to convert it back to the real units. So by using the same scale. So 10 centimeter, if you convert it back, would be converted 10 meter. So then you can write it exactly what it should be. Total displacement is equal to 10 meter, not 10 centimeter, 10 meter. So it is a vector and you need a direction. So that's why you still use a protractor to measure the angle. In this case, in this example, the angle is so small. In my view, this angle is 3 degrees. So I can write it. It is between west toward south. So I can write it as west 3 degrees south. And then next, I can write the answer as a whole thing. I can write the answer like delta D total is equal to 10 meter, not 10 centimeter, 10 meter west 3 degrees south. And the final step would be that piece of cake. Just you do have displacement already now. You divide it by time, then you have 10 meter west 3 degrees south divided by 3.7 is equal to 2.7 meter per second. But you have to do it with a direction because it's a vector quantity. Displacement is a vector quantity, need a direction. Velocity is a vector quantity, need a direction. So 2.7 meter per second west 3 degrees south, and that will be an answer. Now the whole purpose of using this example is to compare the same problem that you can solve using a scale graph diagram with another method that is next lesson, which is a component method. So I'm going to use the same example next lesson to compare how accurate I can be using the scale graph diagram and using a component method, and see which one is more accurate, and we're going to explain why we can use one method and why we can use the other method for the different purpose. So stay tuned, next lesson. See you guys.